Welcome to Lecture B2, in which we will discuss numeric integration and differentiation. First, we'll start with numeric integration. So let's suppose that we have a function f of x and that we want to integrate this function from some point x equals a to x equals b. So here is x equals a, and here is x equals b, and we want to evaluate the integral from a to b of f. Now, we will recall that the integral of f from a to b is simply the area under the curve. So it would be, we could shade it in, and the integral is equal to that shaded area. And so what we're interested in this lecture is trying to find a way to evaluate this numerically. So what we will do is we will divide the interval from x equals a. This is the first step. So first step, divide the interval, we use a capital D here, so we will divide the interval from a to b into subintervals of width h. And I'll put in the word equal just to emphasize that each subinterval will have a width of h. And so if we stick with the notation in your book, it would be like this. We'll call this x1, x2, and then we'll have other x's, and we'll call the last one x sub n minus 1. So, and again, each one of these has a width of h. So this is h, and this is h, and this is h, and all the intervals, subintervals between x2 and xn minus 1 will also be of width h. And now, to estimate the area under each of these, we will proceed as follows. Let's extend vertical lines up from each one of these x's. And what we're going to do is to use the Trapezoid Rule. So that means that we will, for each subinterval, we will look at the line joining where the vertical lines from the two endpoints of the interval intersect with the function itself. So for the first subinterval, we have f of a is here, and f of x1 is there. And so the area of this first subinterval, so we'll say area of subinterval number 1 is equal to we'll have 1/2 of f of a plus f of x1. That's just the average value of f between, if we take these two values, f at this left endpoint and f at the right endpoint, and then we take the average of those two, that would give us the value at the middle, and then multiply that value times the width h, and this would be the area of this first trapezoid, which we hope is a good approximation to the area under the curve from x equals a to x equals x1. Then we'll do the same kind of thing for subinterval number 2. So now we join f of x1 and f of x2. The average of those two will be 1/2 of f of x1 plus f of x2, and we'll multiply that by h, and then we continue with this until we get to the, so I'll say dot 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 here, until we get to the area of subinterval number n, and that will be 1/2 of x, f of x of n minus 1 plus f of b times h. And if we add all of these together, let's say total area, now in calculating this total area, notice that we'll have f of a appears only in this first term. So we have 1/2 f of a. And then we'll have 1/2 of f of x1 and another 1/2 f of x1, because f of x1 appears, x1 is the right side, is the right boundary of interval number 1 and the left boundary of interval number 2. So it appears twice, and we get 1/2 plus 1/2, so we just get f of x1. And likewise, x2 is the right boundary of subinterval number 2 and the left boundary of subinterval number 3. So we'll get f of x2, and so on for all of these up to f of x n minus 1. F of x n minus 1, after all, is the right-hand boundary of subinterval n minus 1 and the left-hand boundary of subinterval n. But then this f of b only appears once, simply as the right boundary of subinterval n. So we'll get a 1/2 f of b, and all of that will get multiplied by h, and there we have it. This is our estimate for for the integral from a to b of f of x dx using the trapezoid rule. So that's quite straightforward. And now let's look at an example. We'll call this example 1. And let's say use the trapezoid rule to estimate and let's say, let me, well, okay, I'll say to estimate the integral from, let's say, from 0 to pi over 2 of sine x dx with let's say perhaps 2 and 4 subintervals. Now, before we proceed, I hope that you will note and will agree from this picture that we would expect in general that the more subintervals we have, the more accurate our estimate will be. And so we will test that idea in this example. In fact, let's go ahead first and calculate the correct answer. So we have integral, so we'll say exact answer well, the integral from 0 to pi over 2 of sine x dx will be equal to minus cosine x evaluated from 0 to pi over 2, and this will be minus 0 minus 1, and so this will be positive 1. So our exact answer is equal to 1. And now let's calculate the estimate using 2 subintervals. Okay, well, remember that the subintervals have to be of equal length. We stipulated that before. And the entire length of the integral of the interval from 0 to pi over 2 is, of course, pi over 2. And so if we're going to have 2 subintervals, then h will be equal to pi over 2. That's the length of the entire interval, divided by 2, which is the number of subintervals. And so h will be equal to pi over 4. Now, remember also from our picture that x1 is equal to a plus h. Here you can see a is the left-hand boundary, and so x1 is a plus h, x2 is a plus 2h, x3 is a plus 3h, and so on. But a in this case, the left-hand boundary of the entire interval, is 0, and therefore we simply have, I'll identify this for you. So a is equal to 0, b is equal to pi over 2, and x1 in this case is a plus h, which will be 0 plus pi over 4, which is pi over 4. And we don't have an x2 because x2 would be x1, excuse me, it would be a, x2 would be a plus 2h, but a plus 2h gives you b. And so we don't call that x2, we simply retain the name b for the right-hand boundary. So now let's see what we get for our estimate. Using this formula here, we would get total area is equal to, in this case, it would be 1/2 f of a plus f of x1 plus 1/2 f of b times h. There's a very short expression in this case because we only have two subintervals, the subinterval from a to x1 and the subinterval from x1 to b. So f of a is being counted as the left-hand boundary of the first subinterval. F of x1 is getting counted twice because it's the right-hand boundary of the first subinterval and the left-hand boundary of the second subinterval. And then f of b is counted once only because it is the right-hand boundary of the second subinterval. And so now we're ready to plug all of this in. We get, remember, and f, of course, is the sine function. So this becomes 1/2 sine of 0 plus sine of x1, which is pi over 4, plus 1/2 sine of b, which is pi over 2. And all of that is getting multiplied by h, which is pi over 4. And so what does this give us? Well, the sine of 0 is 0. And the sine of pi over 2, sine of pi over 4 is the square root of 2 over 2. And the sine of pi over 2 is 1, and 1/2 times 1 is 1/2. And all of that is getting multiplied by pi over 4. And so let's do that. Let's stick that into our calculator and see what we get. Okay, so when I plug these values into the calculator, I get an estimate of 0.9481. And therefore the error using two subintervals is equal to the exact value. And remember, the exact value, exact answer up here is 1. So it's exact answer minus answer obtained with two subintervals. And so this gives us 1 minus 0.9481, and we have an error of 0.0519. Now let's calculate the estimate of the interval, estimate of the integral. Estimate using 4 subintervals. Actually, I think to keep this simple, I'll just make it, instead of 2 and 4, I think I'll change this and just make it 2 and 3. Obviously, if you were going to do a lot of work like this, you would want to write a computer program to do it rather than doing it by hand. So let's change this second one to 3 subintervals. Okay. Now, I would encourage you to stop the video and try to do this yourselves based on what we have already done, just to make sure you have the idea straight, and then come back. Okay, so I hope that you were able to do that on your own, but if not, here is how we would go. H in this case will be equal to pi over 2, which is the length of the entire interval. And this time we divide by 3, since we have 3 subintervals in this case. So H will be equal to pi over 6. Now A is still equal to 0, and B is still equal to pi over 2. And now x1 is equal to A plus H, which is 0 plus pi over 6, which is of course pi over 6. And x2 is equal to A plus 2H, which is 0 plus 2 times pi over 6, which is pi over 3. And there's no x3 because that would be A plus 3H, which would give us 3 pi over 6 or pi over 2, but that's the same as the value for B, and so we keep that name as B. We don't call it x3. So x1 is the boundary between subinterval 1 and subinterval 2, and x2 is the boundary between subinterval 2 and subinterval 3. And now we're ready to have our to calculate our estimate. So we have total area equals 1/2 f of A plus f of x1 plus f of x2 plus 1/2 f of B, all times H. And again, this comes from the formula that we derived right here at the beginning, just before example 1. So now let's evaluate this and see what we get. We'll have 1/2 the sine of 0 plus the sine of pi over 6 plus the sine of pi over 3 plus 1/2 the sine of pi over 2, and all of that will be multiplied by the H that we have for this case, which is pi over 6. And so now let's turn to the calculator and see what we get in this case. Okay, so if we go ahead and plug in the values and use a calculator, we get as an estimate for the total area under the curve in this case of 0.9770. And therefore the error that we have in this case using 3 subintervals is 1, which is the exact answer, minus 0.9770, which is this estimate that we had, or 0.0230. And so notice that if you compare the error we obtained when we used 3 subintervals with the error we obtained using 2 subintervals, it indeed is, we did indeed obtain a more accurate answer. In fact, the error was cut in half by using just one more subinterval. So that's how we would use the trapezoid rule to numerically integrate a function. And now we want to look at the second topic for today's lecture, which is numeric differentiation. One way to obtain formulas for the numeric differentiation of a formula is to return to the work from our previous lecture, in which we derived different polynomial interpolates for a function. And as an example, let's recall the quadratic interpolatory function, or the quadratic interpolate for a function. So you will recall that we had the following. We had the quadratic interpolate, and it was given by the following. We had x minus, now this is assuming, remember, for the quadratic interpolate we needed to know the value of our function f at 3 points. So we'll call those 3 points x1, x2, and x3. So x minus x2, x minus x3 over x1 minus x2, x1 minus x3 times f of x1 plus x minus x1, x minus x3 over x2 minus x1, x2 minus x3 times f of x2 plus x minus x1, x minus x2 over x3 minus x1, x3 minus x2, f of x3. And I'll just remind you of where we had that in our previous lecture. We were calling that y of x. And so here you see the quadratic interpolatory function there for cosine. So returning now to the present lecture. And since we called this y of x before, let's call it the same thing now. So this is y of x. Now, suppose that we want to, well, let me remind you, y of x we're hoping is a good approximation to the unknown function f of x, which is known only at the 3 points x1, x2, and x3, and we're hoping that y of x is a good approximation to f of x in the neighborhood of x1, x2, and x3. So if it is, then we would hope that the derivative of y of x is also a good approximation to the derivative of f of x, and this is how we will get a numerical differentiation formula. So if we take the derivative of y of x, let's see what we'll get. Okay, when we differentiate this first term, we can write the numerator as, think about it this way, of using the product rule. You'll have the first term, x minus x2, times the derivative of the second, which is just 1, plus the second term, which is x minus x3, times the derivative of the first, which is just 1. So altogether we have x minus x2 plus x minus x3, or 2x minus x2 minus x3. That's what we will have in the top, and then everything in the bottom is a constant, so we just have x1 minus x2, x1 minus x3, and then f of x1 plus 2x minus x1 minus x3 over x2 minus x1 times x2 minus x3 times f of x2 plus 2x minus x1 minus x2 over x3 minus x1 times x3 minus x2 times f of x3. And notice also one other thing I want to make sure you understand is we're not differentiating this f of x1 to get f prime of x1. F of x1 is just a constant. It's the value of f at a particular point, just like the denominator here is a constant. And so that's why the denominator in each one of these terms will come right down. It stays the same. And the value of the function evaluated at a particular point just comes down in each case. The only thing that's a function of x is the numerator in each one of these, and we have differentiated the numerator with respect to x to get this formula for y prime of x. Now, the most convenient thing to do is to evaluate, this right now. This is an expression for the derivative at any x in the neighborhood of x1, x2, and x3. But the most convenient thing, and usually what we will do, is evaluate this at a particular x, namely at x1 or at x2 or at x3. And to be honest, we haven't said anything about x1 and x2 and x3 exactly where they are, but we generally we would think of x1 being to the left of x2 and x2 being to the left of x3. That's not really necessary, but that's sort of a convenient thing to think. So let's just go with that idea. Let's assume, maybe I'll do it this way. Assume x1 I'll assume x2 equals x1 plus h and x3 equals x2 plus h. So we're assuming that the points x1, x2, and x3 are equally spaced and the distance between them is h. And let's see what will happen to our formulas in that case. So going with this assumption, we would get, if we wanted to evaluate y prime at x1, this is what we're using to denote the left-hand side, the leftmost value at which we know the value of the function f. Then we would get y prime of x1 is equal to 2x1 minus x2 minus x3 over, now recall, x1 minus x2, since x2 is equal to x1 plus h, x1 minus x2 will be minus h. And actually, let me rewrite the numerator. Rather than writing it as 2x1 minus x2 minus x3, there's a more convenient way to write it. I'll rewrite that as x minus x2 plus x1 minus x2 plus x1 minus x3. Now notice that's exactly the same as 2x1 minus x2 minus x3, but it's a little easier to calculate now since we know that x2 is equal to x1 plus h and x3 is equal to x2 plus h. So let's go with this. Okay. And that will be times f of x1 and x1 minus x3 will be minus 2h. Okay. For the next one, when we stick in x1 here for x, we'll get 2x1 minus x1, so that's x1. So x1 minus x3. And then x2 minus x1 will be h. And x2 minus h3 will be minus h. And this gets multiplied by f of x2. And then finally, when we plug in x1 for x in the last term, 2x1 minus x1 will give us x1. So we have x1 minus x2 over x3 minus x1 will be 2h. And x3 minus x2 is h. And then f of x3. And now we can simplify this further. x1 minus x2 is minus h. And then we have a plus. x1 minus x3 is minus 2h. And in the bottom, minus h times minus 2h is 2h squared times f of x1 plus x1 minus x3 is minus 2h over minus h squared times f of x2. And then finally, x1 minus x2 is minus h over 2h squared times f of x3. And now we can finally simplify all this to get our formula for y prime at x1. And we will obtain minus 3h over 2h squared, so minus 3 over 2h times f of x1 plus 2 over h times f of x2 minus h over 2 f of x3. And this would be our numerical formula for the derivative of x1, the derivative of f at x1, if x1 is at the left-hand edge and x2 is equal to x1 plus h and x3 is equal to x2 plus h. Now let's calculate, well, in fact, I'll challenge you to do this. We now want to, in the same way, use this formula here, I'll put the star by it, use it to calculate y prime at x2 and y prime at x3. So I encourage you to do that, and then we can come back and do it all together. Okay, so y prime at x2, if we plug in x2 for x in this formula, we'll get 2x2 minus x2, so x2 minus x3 in the top. And then in the bottom, x1 minus x2 is going to be minus h. In fact, the denominators will be just as they were here in our first calculation. So we have minus h and minus 2h, and then f of x1. And then the next term, when we plug in x2 here, that one we will write, instead of writing 2x2, we'll say x2 minus x1 plus x2 minus x3. Now notice that's still the same thing as the 2x2 minus x1 minus x3, but it's just going to be, writing it in this way makes it a little easier to evaluate. And then the denominator, just as it was up here, will be h times minus h. And then we'll have f of x2. And then finally for the last term, when we plug in x2 for x there, that 2x2 minus this x2 will give us x2 minus x1 over the denominator is 2h times h. And then f of x3. And so now let's simplify this one. Y prime of x2 will be minus h over minus h times minus 2h, and f of x1 plus x2 minus x1 will give us h, plus x2 minus x3 will be minus h over h times negative h times f of x2, plus x2 minus x1 is h over 2h times h times f of x3. And notice that the middle term here, we have h minus h, which of course is 0, so it will go away. And then for the first term, we have negative h canceling. For the last term, we have h and h canceling. And so we get minus 1 over 2h times f of x1 plus 1 over 2h times f of x3. And this would be our numerical differentiation formula for the derivative of our function at x2, where once again now the assumption is that x2 is right in the middle between x1 and x3. And finally, if we wanted to calculate the derivative on the right hand side, so we have y prime of x3. Let's go ahead and use our formula one last time. So we'll have for this, when we stick in x3 here, we get 2x3 minus x3, so x3 minus x2 in the top, and the denominator is still going to be minus h times minus 2h. And by the way, these formulas that I'm deriving are in your book on page 839. The only difference is that instead of x1, x2, and x3, your book is using x0, x1, and x2. But otherwise, it's exactly the same. So, this is our first term. And then for the second term, when we stick in x3, we'll get 2x3 minus x3, so x3 minus x1 in the top, x3 minus x1, and then the denominator will be just as it is here, h times minus h times f of x2. And then finally, for the last term, the last term is 2x minus x1 minus x2. So when we stick in x3, it's more convenient to write this as x3 minus x1 plus x3 minus x2. So that's what we'll do, x3 minus x1 plus x3 minus x2. And the denominator will still be 2h times h. And now let's finish this up y prime of x3 will be equal to h over minus h times minus 2h times f of x1 plus 2h times h times minus h f of x2 plus 2h plus h over 2h times h f of x3. And so this will end up being y prime of x3 is equal to 1 over 2h times f of x1 minus 2 over h f of x2 plus 3 over 2h f of x3. And that is our formula for the numerical derivative at x3. So these three formulas here, the y prime at x1, y prime at x2, and y prime at x3, as I said, they have the same information as the three formulas given in 14 on page 839 of your text, and they are the values for the numerical derivative when you have three equally spaced points, x1, x2, and x3, and x1 is on the left, x2 is in the middle, and x3 is on the right, and the distance between x1 and x2 is h, the distance between x2 and x3 is h. Then these formulas would give you the values for the derivative at the different points. And sometimes the top formula, since you are using points to the right of x1, is called a right-hand derivative formula. For the second one, x2, since it's in the middle, some people refer to that as a central difference formula. And then for the last one, since x1 and x2 are to the left of x3, some people call that a left-handed or backwards derivative formula. But you don't need to worry about those terms. You just basically need to know how to apply these formulas. And so let's now do one final example for this lecture to make sure it's clear how to apply these formulas. So let's look at this example. We'll say use the formula above to calculate the derivative of sine x at x equals pi over 4 using x1 equals 0, x2 equals pi over 4, and x3 equals pi over 2. So the x at which we are wanting to calculate the derivative is x equals pi over 4, and of course that matches x2. So we want to go up to the formula for y prime of x2. And we see that that formula was y prime of x2 is equal to minus 1 over 2h times f of x1 plus 1 over 2h f of x3. So let's see how this will go. H is the spacing between the consecutive points, which is, in this case, pi over 4. So we get y prime of x2 is equal to minus 1 over 2 times pi over 4 times our function is sine, so sine of x1, which is 0, plus 1 over 2 times pi over 4 times the sine of x3, which is pi over 2. And now let's calculate what this will give us. Well, the sine of 0 is 0, so the first term drops out. The sine of pi over 2 is 1, and so we're left with 1 divided by pi over 2, which is the same thing as 2 over pi. And let's get our calculator and check out the value of that. That gives a value of 0.6366. And now let's compare that to the exact value. Okay, the exact value which is f prime evaluated at pi over 4. Well, the derivative of sine is cosine, so this is cosine of pi over 4, which is equal to the square root of 2 over 2. And that is equal to 0.7071. And so the error would be f prime of pi over 4 minus y prime of pi over 4, and that is 0.7071 minus 0.6366. And we get 0.0705. And that is how we would use these formulas for numerically calculating the derivative of a function. So now let's look at a couple of problems covering this material. Okay, so the problems for lecture B2 are as follows, and they're just like problems that we did in the lecture. The first one, B2-1, requests you to use the trapezoid rule to estimate the integral from 0 to pi over 2 of cosine x dx with 3 subintervals. And of course, again, these are subintervals of equal length. What value do you obtain? And the choices are A, 0.9770, B, 1.0, C, 0.8375, or D, minus 0.7563. And then the second problem is use the formula derived in the lecture to calculate the derivative of cosine x at x equals pi over 4 using x1 equals 0, x2 equals pi over 4, and x3 equals pi over 2. And the choices here are A, 1.0, B, minus 0.9770, C, 0.7563, and D, minus 0.6366. And there will be at least one more problem for the in-class part of the quiz. So that concludes lecture B2, and good luck.